Now let's focus on a specific consequence of turbulence that significantly impacts FSO links, beam wander. As you can see in the diagram, when the size of turbulent eddies in the atmosphere exceed the size of the transmitted beam, the beam experiences random deviations from its intended path. This phenomenon is known as beam wander. Imagine the laser beam as a straight line trying to reach the receiver. However, turbulence acts like invisible forces pushing and pulling the beam in different directions. So consequences of the beam wander include random movement. The beam wanders randomly in space, making it difficult for the receiver to track its position. These random movements lead to position errors, where the beam is no longer perfectly aligned with the receiver aperture. Signal loss. In extreme cases, the beam may wander so far off course that it completely misses the receiver, resulting in a loss of signal. Here, as you can see on the left, the beam travels in a straight line, ensuring a strong and stable signal at the receiver. While on the right, the beam's path is erratic, leading to fluctuation in signal strength and potential loss of communication. Beam wander is particularly problematic for long-distance FSO links, where even small deviations can have significant impact on signal quality. We can mitigate beam wander. We can do such things as beam tracking. Active tracking systems constantly monitor the beam position and adjust transmitter pointing direction to keep the beam aligned with the receiver. We can introduce spatial diversity. Using multiple transmitters or receivers spaced apart can mitigate the effects of beam wander, as it's less likely that all beams will be affected simultaneously. We can also perform aperture averaging. Larger receiver apertures can help to capture more of the wandering beam, reducing signal fluctuations.